Okay, good evening everybody. Thanks for staying a little bit late. It's past my bedtime, I'm sure. My name's John Spicer, I'm from Armstrong Ceilings. I'm the technical manager. I cover the UK, Ireland and English-speaking Africa, which is how we share resource around the world. I've written this presentation as part of the development team on using phase change materials in ceiling tiles. So we will start essentially by finding out when PCMs or phase change materials are in scope on a project, problems we have and when to not use them, and then we'll talk about how PCM materials actually work, how that benefits us, how we then put that into a ceiling, and again the benefits and working a system using a ceiling. Then we'll go through some example projects and case studies, then go through some of the benefits of using PCMs both to the user and to the environment, and then there's a summary and a few references at the end of there if you want some further reading. I've got some questions at the end, but if they pop up, just shout them out. We usually get a few questions along the way. Okay, so a brief history of Armstrong. We've been around for just over 150 years. We're an American company based in Lancaster in Pennsylvania. We employ about 10,000 employees worldwide, and we have about 36 manufacturing facilities around the world. We pride ourselves on having multi-materials, so we're not just a metal ceiling manufacturer, we're not just a mineral fibre ceiling manufacturer. We have those, we have soft fibre, we have wood, mesh, fabrics. Essentially, if there's a ceiling space that can have a product in there, we think that we either have the product or we can source the product to fit that solution. Showrooms, if you're ever in the States, we have a showroom called The Avenue in our headquarters. We have another showroom in Paris, and we have a stand upstairs as well. Okay, so phase change materials, it's essentially we are absorbing excess heat within a room. So when do we need to scope that? Essentially what happens, similar to this room this evening, it was quite cool. The use is, well, people come in, they create a heat load, the equipment is on, the lights are on, we're creating an internal gain. At certain points, possibly in the last seminar, it was getting a little bit too warm and sticky, and the room starts to overheat. So we want to be able to absorb that excess heat, delay your air conditioning coming on, and save some energy. Now to scope that, we need to be able to reset the tiles for the next day, so we get that same storage. So we need some downtime. We need, when the seminar finishes and everyone goes home, the room can settle down. It can cool down naturally. We can introduce ventilation and bring in some natural cool air from outside. We get that purge or the resetting of the tiles. The tile can then absorb the same amount of heat energy the next day. If we get to a point where we can't do that, we just have an expensive ceiling tile. We have an absorption of heat on the first day, but if we can't reset the tiles, they never get a chance to absorb again. So if we have areas that are in constant use, potentially a data centre or A&E in a hospital, where there's a constant heat load, PCM would not be suitable. We need that couple of hours of absorption to delay your air conditioning, or in some cases negate the requirement for it, but we need that downtime to let the heat drop back out of the product. Okay, so first of all, is everyone familiar with phase change materials? Okay, a few shakes of the head, that's fine. Phase change materials essentially are materials that change phase. They go, in this case, from a solid to a liquid, and in that process, they actually absorb heat energy. And that's best shown in this graph here. If you have a standard solid, either a piece of metal or a piece of concrete, if we apply some heat energy to it, over time that will steadily increase in temperature. That's true of the PCM until we reach the melting point of that phase change material, at which point we activate the latent heat. So that's a period of time where the temperature doesn't change. So we are delaying the requirement for cooling in that room. Once that storage is used up, the material will continue to heat up as a sensible heat, so as our concrete or our steel would to start with. So we have a finite amount of storage, which is this latent heat, where we are transferring the requirements or moving the heat away. So if we can do that till 4 or 5 o'clock at night, there is no need for air conditioning to come on. Then we can rely on the downtime and ventilation to reset the tiles. And these are some of the equivalents. So 3 centimetres of plaster with the PCM, covering about 30% of the ceiling space, is equivalent to having the whole space covered in 14 centimetres of concrete or 18 centimetres of brick. So we're able to add thermal mass properties to a lightweight construction. And incidentally, if you're heating concrete, getting the room up to temperature, that concrete is absorbing heat all the way through. So from 5 degrees up to 20 degrees for your set points. And likewise, if the room overheats, the concrete's absorbing it. So if it overheats and it gets to 30 degrees, that concrete may stay at 30 degrees for longer before it gets a chance to cool down. So you have to purge the whole of the concrete all of the way to reduce the temperature. With the PCM, we're only using that storage at the useful temperature, which is from 23 to about 28 degrees over a slight range of temperatures. So we're getting that storage where we're overheating, and that makes the purge quicker as well. So we're only decharging in those brackets of temperature. And this is a typical graph of what we would see in an office space over a period of a week. The red line shows the temperatures within that office without using PCMs. So we're getting peaks and troughs. We're getting certain times of the day where we're getting over 30 degrees, so we're overheating. But at the same time at night, we're dipping right down, we're getting very cool. And what the PCM does is chops off those peaks and cuts the troughs. So we have dealt with the overheating, and then our startup temperature is slightly warmer, so you're not having to add as much heat to that to get the room up to temperature the next day. So we're creating this comfortable zone or a cool zone. And then the general rule of thumb is about 3 kilograms per square metre of floor space, which is about 30 to 50% of the ceiling tiles to be cool zone. The other ceiling tiles would just be an acoustical tile or your services. Now there are a number of different types of phase change materials. There are inorganics and organics, and salt hydrates. Inorganics are naturally occurring. They might be things like palm oils, so they have very good thermal storage, but the main problem is they have very poor fire properties. So if you put that in the ceiling, we can't guarantee that we're going to pass a fire reaction test every time. They're erratic when it comes to fire properties.
If you have quite high acoustic requirements or high hygiene requirements, that preclude incorporating, say, 30% of these? The
majority of the time, if we can get say a Class A sound absorber into the remaining space, we can usually meet the reverberation time requirements. And then in terms of a clean room or adding a kind of a hygiene tile, the cool zone itself is a plain metal tile. So it's easily cleaned. We can actually add a BioGuard type treatment to that antibacterial treatment as well. So we can use it in clean room environments, healthcare, but then we can also use it for acoustics as well. So that even though it's a plain metal tile, the fact we've got an insert behind there gives about 20% sound absorption, which isn't fantastic, but it's better than nothing.
The aluminium?
It's a steel tile, so the heat transfer through it's Okay, not as good as aluminium, but it's still pretty good. The salt hydrates, again, have pretty good absorptive effects for heat. They're also relatively cheap. The problem with the salt hydrates is durability. Because this is a product that melts and then recrystallizes, over time those crystals don't form the full-size crystals, they break up, the liquid gets dispersed. So if they don't form crystals every time, they lose their ability to absorb heat. So there is an erosion of its ability to absorb heat over time. Now the organics, yes, we're using a hydrocarbon, that's relatively bad for the environment, but we are able to manipulate that to exactly what we need. In this case, we're using micronal, which is a PCM produced by BASF, a chemical company. It's a wax capsule that's then micro-encapsulated. So there's a plastic core polymer that wraps around that plastic and gives us some durability. We don't have to worry about fire performance. A bag of the PCM, if we were to bring that into the room, would just look like a powder. There's no liquid or wax that can get out of the product. And the micro-encapsulated PCM is not just used by ourselves. There are other products out there, clay panels, plasterboard. Again, some of the issues around other products is being able to get that purge, able to reset it. With the plasterboard manufacturers, you need to put an extra layer of plasterboard to get the fire performance, which is actually like an insulator. It's reducing the performance. There's gypsum products, magnesium cement products, and then various others that are in development. So this is very much a technology that's been around since the 1950s, but it's only more recently that we've been able to micro-encapsulate it and make it into a useful building product. And this is what the wax capsules look like under a microscope. You can see the paraffin core and then this protective shell which maintains that melting and solidifying all happens in one space. The product cannot leak out. And we have a couple of set points that we can have for that melting point, 23 degrees or 26 degrees. In the case of cool zone, we're using 23 degrees, and we're saying there that the room may get to 24, 25 before that starts to melt, or the heat gets through to the product. So we're looking at those 25, 26 to 28 degrees as the useful zone where we're overheating. Durability, we've mentioned there that we've got the micro-encapsulating to maintain its reaction, that efficiency isn't lost. We've accelerated the process, so one day is a melt and then a solidify as one cycle. We've sped that up, so we're doing quite a few a day, and we're already over 10,000 cycles, equivalent to about 30 years. So this product has a guarantee for 30 years. It will probably continue to work for a longer period of time. We expect the change of use of the building to come into effect before this product actually starts to lose its ability to absorb heat. So what do the tiles look like? I mentioned very quickly. We have a plasterboard insert that contains the PCM. We use the plasterboard because we can cut it quite easily to shape. We then have a commercial product. That's incorporated in two metal tiles. One has an 8mm drop, one has a 16mm drop. So you can choose which way around you put it into the grid as to whether that's an 8mm drop or a 16mm drop. Two metal tiles to make sure that we get the fire reaction performance. It means we can use it in escape corridors, we can use it in any area of the building. The only place we couldn't use that was in the London Underground, where we need an A1 fire performance. And this is a picture of a typical installation. So there's generally a grouping of the cool zone tiles or the plain tiles, and then we put a bank of the acoustical tiles in there. And you've got your other services that can also fit in there. The tiles themselves can actually go in any position in the ceiling. They don't have to be grouped in a particular orientation. It generally is grouped just to make it more aesthetically pleasing. And you may actually choose to put it over a heat source, over a printer or something that's generating a lot of heat to have a local impact. I've mentioned the fire reaction performance. We achieve that by using the microencapsulation by putting it into a metal ceiling tile. Because of that, we don't really want to cut the tiles. There's a benefit to keep these as full tile units. If the room changes configuration or use and there's no longer an overheating issue, we can actually pick those tiles up, move them, put them somewhere else. Something you probably couldn't do with an air conditioning system.
One quick question about the fire reaction and whatnot.
Yep.
In a suspended ceiling system, often you can get suspended ceiling systems that provide structural fire protection.
Fire resistance, yeah.
Presumably this can't be used
No.
for that type of ceiling system.
We don't think we would pass to be usable, so it's say 30 minutes to steel. We have a number of other ceiling tiles that can do that. In that case, we would say not to use the PCM. We have other solutions, but you may get your protection through intumescent paint to the steel or plasterboard before then. Sorry.
Does it come in your standard 600 module?
The product as we have it is a 600 unit, available in tecular or microlic, so 15 or 24 mil grid. So there's no health concerns. It's not a product that's going to be able to leak out there if there is a fire. The steel tile can be recycled the same way any other steel is on site, and then the plasterboard can actually go into the plasterboard recycling route as well. So there's no reason for this to go into landfill, and the benefit might be that some future plasterboards might get some PCMs in them. They are, however, quite a heavy tile. They're about 9 kilos a panel, so it's about 25 kilograms per square metre. So there's a bit of grid strengthening we need to do. Generally speaking, if it's a standard installation, your main runners will be at 1200 sensors, and your hangers will be at 1200 sensors. Where we're putting the cool zone, we want to add some extra hangers in at 600 sensors. And that will include a hanger in the middle of the 1200 crossing. Well, this is a new build, so it's a new installation. We're putting the grid in. We'd put the main runners at 600 sensors, and then just our hangers at 1 metre sensors. So there is a small overhead to strengthen the grid. The evolution of this product will be to have the same storage but a slightly lower mass, so we can just drop it into any ceiling tile. And maintenance, unlike your air conditioning where there might be a case of changing filters, changing units after a period of time, there's no maintenance other than treating it like a standard ceiling tile. So a little bit of dusting, the odd clean, that's all that you need to do.
You mentioned there's an overhead to the suspension system. Clearly the amount of product that's involved will be an overhead cost increase to say against a Viaguard or a Pro or something.
Absolutely.
What's the sort of rule of thumb percentage on that?
If you're looking at a standard metal tile, it might be £35 a square metre. This is £150 a square metre. So the key is not to look at this as a ceiling tile. It's much more than that. It's to take your ceiling tile, your ceiling budget, and your HVAC budget, merge the two, and you actually show a saving over the two. Of smaller air conditioning units, so you design it as a system, by being able to reduce the ductwork, the units, etc. There's a cost saving, or by not putting air conditioning in at all. So this slide is showing how the tiles look with a thermal imaging camera. The tile on the right is just a standard metal tile, no infill, and that's showing quite a hot surface. It's 26 degrees. In the same room, the PCM tile is showing a surface temperature of 22 degrees. And that's because the PCM insert is pulling the heat through the metal. So we're actually having a cooling radiant effect on that panel as well. So the perceived temperature in that room is lower because you've got a cold surface. So there's some benefits to thermal comfort, not just your potential saving on your energy bills. And then this graph below is showing a ceiling without PCM heats up, your air conditioning kicks in, it cools for a period of time and then it clicks out, the room heats up again, it cools, it heats up. So there's a constant noise, a constant draft of the air conditioning clicking in. And what we want to be able to do is to delay the requirement for air conditioning and create a nice, even temperature. And because we're creating that nice, even temperature, we're not having that fluctuations, you can actually put up with a slightly warmer temperature. So the set point might actually be 24, 25 rather than the 23, 24. Now, I mentioned about being able to reset the tiles. The cheapest and the easiest way to do that is to bring in the nighttime air. So typically in the UK we are getting below 20 degrees. Like tonight, I believe it's -2, a little bit later on, maybe not in London. But we can make use of that very cold air, bring it through the ventilation system, pass it over the ceiling, and cool those tiles. So we're able to reset just enough to reset that tile back to square one, back to maximum storage for the next day. Now to do that, there's some limitations in geography as to where those nighttime temperatures get to the right temperature. So we'll see a market there of North America and Northern Europe. So at the time we get to Southern Europe, Spain and Italy and places like that, the nighttime temperature might be getting just a little bit too warm to be able to purge every single night of the year. That's not to say that we can't put it in those places. We're talking at the moment about a project in Dubai where the desert nighttime temperature is obviously very cold. The fact that the solar gain during the day probably means that the PCM is used up very quickly is a different matter. But we're also talking to a company in California who are using a heat pump to be able to get that purge. So there are other technologies of getting that cooling for free and not just relying on the outside air. So this graph is talking about the enthalpy of PCM. So as you can see, as we go up the temperature scale, there's not a lot that happens to the material. Then we suddenly get to 23 degrees and we reach the melting point of the material, and there's this sudden spike, and that's its ability to absorb that excess heat. And then as we get past its useful temperature, that the material is completely melted, again there's not much storage that comes in. So we've got the start of the day, people coming into work, switching on their computer, switching on the lights, and we're able to absorb that excess heat. We're only absorbing heat when that room temperature gets to 23 degrees. So if that doesn't get to 23 degrees until lunchtime or after lunch, we're then only needing to absorb the excess heat in the afternoon, and we can see through to, say, 5 o'clock when everyone goes home without having to use air conditioning. And certainly the majority of those days in the year, you could probably get through without having to use air conditioning. Where we have a higher heat load, that heat absorption, heat capacity is used up a lot quicker, and then your air conditioning has to kick in to maintain a temperature. But then we need this purge, the downtime, to reset the tiles for the next day. So if we talk about some of the carbon credentials of cool zone, if we say that for every 1 square metre of cool zone that's produced, we're creating 6 kilograms of micronized use, so we're using roughly 1 kilogram of CO2 is producing our product. If we then put that into the model and we're saying over the 30-year life of that ceiling tile, we're able to delay air conditioning by a certain amount, that energy or that electricity that powers that air conditioning is the equivalent to 10 kilograms of CO2 that would be producing that electricity. So we have a carbon ratio of 1 to 10, so we're actually a carbon negative product. So where can we use cool zone? Where can we use PCM? The biggest sector for us and the easiest to put this in is education. Generally speaking, there is a move to not use air conditioning. We can use passive solutions. We can use things like natural ventilation, and the two work in tandem. So we get that nighttime purge through the natural ventilation, but we're giving you that storage and delaying the requirement for cooling by using the cool zone. Again, offices, good examples. Old 1950s buildings where you have maybe a slightly dated HVAC system, very inefficient. We can prolong the life of that system by delaying its requirement to use. So you have a bigger impact in terms of the energy you can save. Inefficient systems, if we're not using them, we're saving more energy, more money. Where we have a more modern system, there's certain savings, but it's not going to be as big as an inefficient system. But that might be something that could be designed in as a new build so that you actually minimise the amount of air conditioning you use, the number of ducts, the size and rating of your air conditioning system. Healthcare. We initially said, well, no, we can't put this into healthcare, it's a 24-hour environment. But even within big hospitals, there are zones that are only working 9 till 5, consultancy rooms. And we can certainly see a benefit there, where we don't maybe even need to use air conditioning at all. Retail, so bars, restaurants, where there's a sudden influx of people for a certain period of time, you'd have to overrate your, or rate quite highly your air conditioning to be able to deal with that sudden increase in heat load. By offsetting that with the cool zone, we're able to absorb for a period of time. Those people leave by the end of the evening, and the room then has a full day to settle down and to cool back down again. And that's the same with leisure. So you talk about theatres, where there's 150, 200 people that come into a space. We can add the cool zone in there, particularly in some cases where there's a listed building. We don't want to be knocking too much services through walls and other fixtures and fittings. We can actually deal with that overheating.
Can it be incorporated into different applications for like wall panels or?
Absolutely, that's something we're looking at the moment, is to have a metal wall panel system that has that. The plasterboard manufacturers that currently use it as a wall panel system have to have another layer of plasterboard over the top to get the fire protection. So you're blocking its ability to purge and its ability to absorb in the first place. So having that as a metal tile with an air gap behind, we can get the purge and maximise its ability to absorb heat. So yeah, definitely. Other areas we're talking to people about is actually to get it into furniture, so under desks and things, so it's localised to where your PC is. So you're adding thermal mass to lots of different elements within the room. And then these are some examples of what you would need to do to make the cool zone work to get that purge. So a naturally ventilated building, it's very easy. We add in the PCM, whether that be in a canopy form, a baffle or a ceiling. And all we have to do is just to open the window to get the purge. For a chilled ceiling, generally speaking, they're quite efficient to start with. And we have a business in Switzerland that make chilled ceilings. We're looking to add the PCM into the chilled ceiling, so you have an active solution. So we don't then rely on, can we get a purge? Are we able to get ventilation? We actually have a system that you just put in place and it works every time. And then these are some worked examples for different types of air handling systems and what you would want to do. And essentially, we want to get a ducted extract. We want to be able to get that hot air out of the void. So either have a ducted air extract, or we introduce ventilation into the void space so we can promote some airflow. Because that heat in the cool zone actually wants to go up for natural convection. If we can get an airflow that passes over the back of the tile, we can actually circulate that back into the room, get a better mix, some turbulence that helps to reset the tiles a bit quicker. Okay, so what are the benefits of using PCM? Well, we're reducing energy consumption, therefore we're saving money. We're adding thermal mass into lightweight structures. So if we go back to the school situation, there's priority schools at the moment where they're designing exposed concrete to manage their overheating. Again, we're not using air conditioning, so we have an issue with acoustics. If we're able to put the same storage capacity in the thermal mass into a lightweight construction, we can then go into timber structures, into steel structures. We can reduce the cost of that project per square metre, and we can probably build it in half the time. We're also then reducing the load on the air conditioning, or the need for air conditioning in the first place. The way to look at air conditioning is it's always costing you money. You have the capital cost to install it, you have the running cost, the maintenance cost. So you never actually get a downtime when you're not using it, when you're not having to pay money out. If we can combine that with PCM, we are essentially losing you less money. So you've got a one-off capital cost for the PCM, there's no maintenance cost and there's no running cost. So we can delay the use of your air conditioning with saving you money. And then the other thing we want to do is be able to insulate that building as well. If you have a very leaky building that heats up during the day, it will also release all of that heat at night, so you're not actually storing it or saving energy. So it's important to get the right insulation, and that includes solar shading during the day. We have a low embodied energy, low carbon footprint for that product. But it also works in the winter time. So if we're able to absorb that heat going into the afternoon, we can actually turn off our heating that little bit earlier, so we can see through to the end of the day. The product just drops the heat back into the room, maintains the temperature. That also means that for the start-up the next day, the room temperature is slightly warmer, and it's not costing you as much in your heating bill to bring that up to temperature. Your heating will also cycle on less often as the storage heater effect, and it absorbs the excess heat, releases it back into the room. Your thermostat doesn't register until a little bit longer before you have to heat the space. So the other important thing is the number of days that you're reaching overheating, or over 26 degrees. And in this example, along the bottom is the number of days this particular room was overheating. And you can see that's quite a number of days every month from April to August. When we use PCM, we're able to lock those peaks, that overheating. And yes, we still get some days that are overheating, particularly warm days where we've just overcome the strength or the storage of the PCM. But we've really knocked down the number of days that are overheating. So that suddenly lets you comply to certain BB 101 or other Part L regulations. We're able to suddenly make a building pass. Okay, so our first case study is Central London Architects. Can't name names, but this is a basement office. They use a ventilation system that passes through every room in the basement and then is exhausted back out into the street. So each room gets progressively warmer as it picks up the excess heat. So our study was in the back left-hand corner. This is one of the largest offices, and this was where they had a meeting of all the staff on a Friday. Now that meeting typically lasted 20 minutes, and they didn't get everything done because it was too hot. What we did was to add some of the cool zone into the ceiling, and then monitor what was happening. So we were monitoring the room temperature, we were monitoring the temperature of the air that's passing in and out of that room. And what we noticed was the architects had their Friday meeting, but it was lasting an hour and a half. And maybe they should have been getting back to work, but they were certainly comfortable in that room and were able to get through what they needed to do. And then the second case study is actually an independent test we've done with BizRear. In this case, it's a thermal test chamber, so we are creating those conditions and we're testing the different purge times. So we're using dim-man heaters to create that artificial heat load, and then we're trying different air conditioning types or different ventilation types, different air temperatures, different flow rates to see what happens to the purge rate. And what we found was if we have a very low temperature of air, so the outside air that we have this evening, we can bring that into the space, we can purge the tiles very quickly. In this case it was an hour and a half. Where we have slightly warmer air, or we have a slightly slower flow rate, that purge time takes a little bit longer. But typically we've got the whole night to play with. So it doesn't matter, as long as that tile is reset for 9 o'clock, it doesn't matter what strategy we use. And in some cases, the coldest part of the night is actually between 5 and 6 in the morning. So if you can do a super purge at that time of the morning, it might be as simple as a caretaker coming in and opening a window, or it can be a bit more sophisticated in that we have thermocouples in the tiles that tell you whether it's molten or solid. It tells you where it needs to be purged or not, and then that can actually automate the ventilation to activate the purge. I don't expect to be able to read this at the back, but this is kind of an opportunity matrix for different systems. So we start off at the top, very simple passive solutions, natural ventilation. The cost of putting the cool zone product in there is relatively low, and the complexity in terms of what you'd have to change to the existing system is also quite low. And we move through a number of different systems until we move on to things like chilled ceilings, chilled beams, which are essentially very efficient. And this might be a great big headquarters building where we only want to put the cool zone into one particular area. That means that there may be more complexity. We may have to put BMS controls onto every single room just to be able to control one room. So the costs and the complexity go up. So if you have a passive solution, a natural ventilation, this is a no-brainer. You should be adding the cool zone in there. You see the instant effect. If it's a more complicated building, you might want to just use it in areas where you haven't got air conditioning, such as meeting rooms, where it can have an effect on a meeting that lasts an hour and a half, and then has the time to naturally reset. So if the room cools down below that 23 degrees naturally, we can get that purge without having to actually add anything to it. So we're a passive solution. Cool zone is reacting to its surroundings. So it's important to design the system around that. We don't want people to be changing the thermostat to 22 degrees in the summer, so your air conditioning comes on at 22 degrees. The cool zone does not get a chance to work at that point. It only starts to absorb at the melting point of 23. Likewise, in the winter time, if you put your heating on at 26 degrees, you're having to overcome the storage before you're heating the room. So there's some designs in there. And we were talking to some consultants recently, and they were just using dummy boxes on the wall. So people had the placebo effect of turning the temperature up or turning the temperature down, but it wasn't affecting the system. So we quite like that. So we are making better lettable buildings. If we can reduce the amount of ductwork we have, we can create a higher floor-to-ceiling height. We can potentially, in a high-rise building, add an extra floor, or we can increase the ceiling height enough so we get an extra rent. The green taxes that are coming in, we can actually offset those costs, and you also have a portable asset. So if you're a business that's renting a space and your landlord will not put air conditioning in because the space is overheating, you're probably not going to spend that money on air conditioning knowing that you might be moving out. But you might choose to invest in the cool zone system knowing that you can take those tiles with you to a new building. So you have a portable asset. So that's particularly useful for people like FM managers who can have a store of these tiles and then go and put them into problem areas. Likewise, if the room changes use or configuration, you just move the tiles around to where they're needed.
What happens with the strengthening of the tile if you're moving the tiles around?
So it's a drawback certainly with Mark 1. We're hoping that the next one will be a case you can drop it in anywhere. You need to make sure that the facilities manager knows that if they're moving around, there's a potential to need to strengthen the grid as well. Now the difficult one is calculating payback. We don't have a product that says this is a 2-year payback, it doesn't matter where you put it. Because this is a passive solution, it's reacting only to the system it's in. It depends a lot on the design and age of the building, how leaky the building is, the HVAC system that's being used, how efficient it is, what your energy costs are, and what your purge strategy is. So if you get natural ventilation, there's no cost. But if you're not in that position, you're actually having to make use of, say, a nighttime tariff for your cooling, so there's a smaller saving, then the payback is going to be much longer. And then if you're designing it as a new build, or if you're retrofitting this into a product, into an existing building, there's going to be differences as well. So for a new build, we can design out air conditioning, and the saving is what it would have cost to put that air conditioning in the first place. With a retrofit, that system is already there, you're just making it more efficient. But the biggest one that doesn't come into the payback is that thermal comfort for the users. So they're not feeling a draft, they're working at a nice comfortable temperature, and there's this cooling radiant effect of having a cooler surface in the ceiling. So by conserving energy, we're reducing the dependency on fossil fuels. Yes, we use green energy, but that's such a small amount in the UK at the moment. We're still reliant on fossil fuels to bring that in. And those prices for that fuel is only going to go in one direction. We're able to lower your carbon emissions taxes. We're able to shift the requirement for cooling to make use of cheaper tariffs. So, in summary, we are using phase change materials to improve the thermal storage within a building. We're adding thermal mass to a lightweight structure. The whole process is endothermic, so it's taking in heat or it's throwing it out, depending on the phase that it's moving from. So we're actually able to manage overheating within spaces. This is a list of references. If there's anyone that's interested in some further reading, I can certainly circulate these. Useful when we're putting the presentation together, but also on research of what's gone before. That is the end of the presentation. Are there any questions at that point?